Newton's three laws of motion. Sir Isaac Newton was one of the most influential scientists and mathematicians that ever lived. He was born in England on the 25th of December 1643. He was born the same year that Galileo died. He lived for 85 years. He attended the Free Grammar School and then went on to Trinity College, Cambridge. Newton worked his way through college. While at college, he became interested in math, physics, and astronomy. Newton received both a bachelor's and a master's degree. While Newton was in college, he was writing his ideas in a journal. Newton had new ideas about motion, which he called his three laws of motion, which we are going to talk about today. His ideas became the basis for modern physics. He built upon ideas put forth from the works of previous scientists, including Galileo and Aristotle, and was able to prove some ideas that had only been theories in the past. He studied optics, astronomy, math. He invented calculus. He also had ideas about gravity, the diffraction of light, and forces. Newton's ideas were so good that Queen Anne knighted him in 1705. His accomplishments laid the foundations of modern science and revolutionized the world. Here you will develop an understanding of each of Newton's three laws of motion. Newton's first law of motion. Every object in a state of uniform motion tends to remain in that state of motion unless an external force is applied to it. This is often termed simply as the law of inertia. An object at rest will remain at rest unless acted on by an unbalanced force. An object in motion continues in motion with the same speed and in the same direction unless acted upon by an unbalanced force. What this actually means is there is a natural tendency of objects to keep on doing what they are doing. All objects resist change in their state of motion. In the absence of an unbalanced force, an object in motion will maintain the state of motion. This simply means that things cannot start, stop, or change direction all by themselves. It takes some force acting on them from the outside to cause such a change. The key point here is that if there is no net force acting on an object, that is, if all the external forces cancel each other out, then the object will maintain a constant velocity. If the velocity is zero, then the object remains at rest. If an external force is applied, the velocity will change because of the force. So that is the first law of motion. Newton's second law of motion. The relationship between an object's mass, m, its acceleration a, and the applied force F is F is equal to ma. Acceleration and force are vector quantities, which means that they have magnitude and direction. In this law, the direction of the force vector is the same as the direction of the acceleration vector. Acceleration is produced when a force acts on a mass. The greater the mass of the object being accelerated, the greater the amount of force needed to accelerate the object. Everyone unconsciously knows the second law of motion. Everyone knows that the heavier objects require more force to move the same amount of distance than lighter objects. So this law defines a force to be equal to change in momentum, that is, mass times velocity per change in time. Newton also developed the calculus of mathematics, and the changes expressed in the second law are more accurately defined in differential forms. For an object with a constant mass m, the second law states that the force is the product of the object's mass and its acceleration a. For an external applied force, the change in velocity depends on the mass of the object. A force will cause a change in velocity, and likewise, a change in velocity will generate a force. The equation works both ways. In the simplest of cases, a force applied to an object at rest causes it to accelerate in the direction of the force. However, if the object is already in motion, or if the situation is viewed from a moving reference frame like a train, that body might appear to speed up, slow down, or change direction depending on the direction of the force and the directions that the object and reference frame are moving relative to each other. Newton's third law of motion. The third law states that for every action, that is force, in nature there is an equal and opposite reaction. In this picture, you can see the rocket's action is to push down on the ground with the force of its powerful engines, and the reaction is that the ground pushes the rocket upwards with an equal force. In other words, if object A exerts a force on object B, then object B also exerts an equal force on object A. Notice that the forces are exerted on different objects. The third law can be used to explain the generation of lift by a wing and the production of thrust by a jet engine. This means that for every force, there is a reaction force that is equal in size, but opposite in direction. That is to say that whenever an object pushes another object, it gets pushed back in the opposite direction equally hard. Forces always occur in pairs. So when one body pushes against another, the second body pushes back just as hard. For example, when you push a cart, the cart pushes back against you. When you pull on a rope, the rope pulls back against you. When gravity pulls you down against the ground pushes up against your feet. And when a rocket ignites its fuel behind it, the expanding exhaust gas pushes on the rocket, causing it to accelerate. If one object is much more massive than the other, particularly in the case of the first object being anchored to the earth, virtually all the acceleration is imparted to the second object, and the acceleration of the first object can be safely ignored. For instance, if you were to throw a baseball to the west, you would not have to consider that you actually caused the rotation of the earth to speed up ever so slightly while the ball was in the air. However, if you were standing on roller skates and you throw a bowling ball forward, you would start moving backward at a noticeable speed. The three laws have been verified by countless experiments over the past 3 centuries, and they are still being widely used to this day to describe the kinds of objects and speeds that we encounter in everyday life. They form the very foundation of what is now known as classical mechanics. Thank you.